Why 2-hour drone flight still feels out of reach, and how solar power changes the conversation. Imagine a drone that doesn't rush its mission. It doesn't constantly calculate how far it can go before a battery warning appears. It doesn't need to cut inspections short or return home early. Instead, it stays in the air, steady, reliable, and present for hours at a time. Not 30 minutes, not 40 minutes, but 2 full hours of continuous flight. For anyone working in environmental monitoring, infrastructure inspection, mapping, or emergency response, that kind of endurance would change what drones are capable of. It would turn drones from short burst tools into persistent aerial platforms. Yet despite rapid advances in sensors, cameras, and autonomy, flight time remains the hardest limitation in modern drones. The question seems simple. Why can't today's drones fly longer? And more importantly, could solar power be the key to unlocking extended flight? The battery barrier. Every drone faces. Most consumer and professional drones today rely on lithium-based batteries. These batteries are compact, relatively lightweight, and far more capable than they were even a decade ago. Each year, energy density improves incrementally, squeezing more capacity into the same physical space. But physics sets a hard boundary. A high-end multi-rotor drone typically carries a battery in the range of 80 to 90 watt-hours. Under real-world flying conditions, wind, maneuvering, hovering, payload weight, that translates to roughly 25 to 40 minutes of flight time. The reason isn't inefficiency, it's gravity. Multi-rotor drones must continuously produce lift just to stay airborne. Unlike airplanes, they don't glide. Every second in the air requires constant power, whether the drone is moving forward or hovering in place. On average, a drone of this class consumes around 150 watts while flying. When you divide the available battery energy by that power draw, the limit becomes unavoidable. To fly for 2 hours, the drone would need close to 300 watt-hours of usable energy, 3 to 4 times more than what it currently carries. Why just add a bigger battery doesn't work? At first glance, the solution seems obvious. If battery capacity limits flight time, why not simply increase the battery size? The problem is that weight and energy are tightly coupled. A larger battery adds mass. More mass means the motors must work harder to generate lift. That increased power demand drains the battery faster, erasing much of the benefit of the added capacity. This creates a feedback loop that engineers know well. Adding energy storage increases weight, which increases power consumption, which reduces endurance gains. Beyond a certain point, the trade-off becomes counterproductive. In multi-rotor designs, this loop is especially unforgiving. There is no aerodynamic lift to offset weight. Everything is paid for in watts. The solar question, elegant, logical, and limited. Given these constraints, it's natural to ask whether solar power could help. The appeal is obvious. Sunlight is free, abundant, and renewable. If a drone could harvest energy while flying, even partially, it might extend its time in the air without increasing battery weight. In theory, the idea is elegant. In practice, it runs into a simple geometric problem. Surface area. A multi-rotor drone has very little usable space for solar panels. Even if you covered the top of the fuselage, arms, and any flat surface available, you might achieve around zero point 0.1 square meters of panel area. Under ideal midday sunlight, using high-efficiency solar cells, that area might generate roughly 10 watts of power. 10 watts. Compared to the 150 watts required just to remain airborne, that contribution is marginal. Solar power in this configuration can slow the rate of battery drain slightly, but it cannot fundamentally change the endurance equation. Solar panels alone cannot turn a 40-minute multi-rotor into a 2-hour aircraft, not with today's physics and not with this design. Rethinking the problem instead of forcing the solution. This doesn't mean solar-powered drones are unrealistic. It means the question needs to change. Instead of asking, how do we add solar panels to existing drones? Researchers and engineers ask a more productive question. What type of drone actually benefits from solar power? The answer leads away from multi-rotors and toward fixed-wing aircraft. Why fixed-wing drones change everything. Fixed-wing drones operate under fundamentally different aerodynamic principles. Once they reach cruising speed, they generate lift from their wings rather than relying solely on motor thrust. That means they don't need constant high power just to stay in the air. As a result, a fixed-wing drone carrying a similar sensor payload can cruise using significantly less power, often in the range of 100 to 120 watts, and sometimes even lower under optimal conditions. But the real advantage lies in the wings themselves. Wings provide surface area, and surface area is exactly what solar panels need. A fixed-wing drone with a 2-meter wingspan can easily offer half a square meter or more of usable space for solar cells. Under the same sunlight that provided only 10 watts on a multi-rotor, those wings can generate 60 to 70 watts of continuous power. Suddenly, solar energy is no longer a novelty. It becomes a meaningful contributor. The hybrid approach, VTOL, meets fixed wing. Fixed-wing drones do come with their own limitations. They typically require runways or launch systems, which reduces their flexibility in confined environments. To overcome this, engineers combine the strengths of both designs. The result is the hybrid VTOL, vertical takeoff and landing solar drone. This type of aircraft uses multi-rotor propulsion for takeoff and landing, allowing it to operate from small or unprepared locations. Once airborne, it transitions to fixed-wing flight for efficient cruising. Solar panels integrated into the wings provide continuous energy input during flight. Each component plays a role. The multi-rotors provide vertical lift when needed. Fixed wings reduce power consumption during cruise. Solar panels offset a significant portion of energy demand. Together, they create a system where extended endurance becomes realistic rather than theoretical. What the numbers look like in practice. Consider a simplified example. A solar-assisted fixed-wing drone cruises at approximately 120 watts. Under good sunlight, its solar panels generate around 70 watts. That means the battery only needs to supply the remaining 50 watts. Over a 2-hour flight, the battery provides about 100 watt-hours of energy, well within the range of modern lithium batteries, even after accounting for reserves and inefficiencies. The solar panels don't replace the battery. They extend it. This distinction is critical. Solar energy smooths the power curve, reduces discharge rate, and allows smaller batteries to deliver longer missions. When combined with intelligent flight control systems that adjust speed, altitude, and heading to maximize solar exposure, endurance increases further. Why 2 hours matters more than it sounds. Doubling flight time doesn't just add convenience, it changes how drones are used. Longer endurance means fewer landings and relaunches. It enables larger survey areas and longer inspection routes. It allows continuous monitoring instead of fragmented data collection. For environmental research, this means tracking wildlife or vegetation without repeated disturbances. For infrastructure inspection, it means covering pipelines, power lines, or coastlines in a single mission. For disaster response, it means staying overhead longer when ground access is limited. At that point, drones stop being short-duration tools and start behaving more like aerial platforms. Can today's consumer drones reach this level? A consumer multi-rotor drone in its current form cannot realistically achieve 2 hours of flight, even with solar assistance. The limitation isn't a lack of innovation. It's a consequence of physics, aerodynamics, and geometry. But by rethinking the design, by embracing fixed-wing efficiency, hybrid takeoff systems, smart energy management, and solar augmentation, the industry is steadily moving toward longer endurance flight. The future of drones isn't just about better cameras or smarter software. It's about staying in the air longer. And in many cases, the answer isn't a bigger battery. It's learning how to fly with the sun.